So welcome back. We are now in lecture number 2, Math 140, Business lecture number 2 on January 27th, 2022. And let's quickly recap just some of the basic stuff that we did last time. Last time we started with individuals. Those are the objects of study. And variables. Those are the attributes, the characteristics of those individuals that we might care about. The variables themselves fell into two categories. There was categorical variables versus quantitative variables. Categorical variables are described via pie charts and bar graphs, both of which we I looked online. I just showed you a couple pictures and it was like, oh, okay, well, that's kind of obvious. And then we talked about some of the different displays that we would use for quantitative, namely a histogram, a dot plot, a stem plot. It was mentioned a scatter plot, although technically that's for two quantitative variables, not one. So we'll kind of, I know I wrote it last time, but I'll hold up this time. And that's basically it. Now, whether we're dealing with a categorical variable or a quantitative variable, throughout the semester, you're going to quite often hear the term the distribution of a variable. And this is a very important concept, the distribution of a variable. And it's slightly different in terms of how we use it for categorical versus quantitative. And even within quantitative, we can break it up into two different types. But the basic idea is that the distribution of a variable tells us what values the variable takes and how often it takes those values. And I put in parentheses here, even though the book doesn't say it, I'm going to put into parentheses how likely each value is. So not only is it how often, that's if you actually perform some kind of experiment, take a survey, take a sample, you actually have results. Then I can say, oh, I got this result this many times, I got this result that many times, and so on. But even in the case of not doing an actual example, if I talk about the distribution of flipping a coin, then if I referring to the distribution of flipping a coin, then what are the values? What are the outcomes that the coin can have, heads or tails? Those are the different values that the outcome can be. And each one has a likelihood of, let's say, 50%. If it's fair, that would be the distribution of the flip, the distribution of that experiment. Whereas since we're not up to that type of situation yet, now we're talking about actual outcome distributions, where you have your data and you say, oh, okay, I got this many times, I got this many times, I got this many times, and so on. So the distribution at this point of a variable is all about the outcomes of an experiment. Okay, so in the book, and for some reason I'm having difficulty sharing my screen on my computer. I don't know why. But if you do have the, well, I don't think any of you have the book yet, but for later, on page 17, there's an example of a data taken from 1.5 million full-time first-year students enrolled in colleges and universities in 2011. And the question of interest for this particular poll or a survey was the field of study. And there's some options: arts and humanities. There's biological stuff. There's business stuff. There's education, engineering, the physical sciences, professional. I don't know what that means exactly, but professional, the social sciences, the technical fields, and other / undecided. So my knowledge is pretty limited to the things that I'm, knowledgeable about, which is like math, science, chemistry, chess, those kind of things. So what exactly is professional? Anyone know? That's it specifically. I really have no idea.
I'm just as lost as you on it.
I'm sorry?
I'm just as lost as you are on it.
Yeah, like all the other ones, I know what they are. I don't really know what professional means, but whatever. It's just an example. So they have the different fields of study, and then they have the percent of students who are in those fields. And the first one is 11.0, 10.9, 14.9, 5.9, 12.0, 3.7, select few, the proud, the brave, 14.9, 12.1, 1.0, and 13.5. Now, when I add up those numbers, what do you expect those percentages to add up to?
100.
100, yeah.
It should be 100%, but if you actually add them up, you get 99.9%. Now, when I ask my students every year, where's the other 0.1%? I always get the answer, oh, it's others. It's the people who didn't answer. But no, we already have those. That's those. This is everyone. We're not missing anyone. We're not missing 0.1% of our answers. These are all of the answers. So why is this not adding up to 90 to 100%?
Because no statistic is
miscalculation.
perfect.
I'm sorry, one second. I heard two different things. One of you go, then the other goes. What?
Miscalculation. Yeah.
Well, if it's a miscalculation, then we can just redo it. But no, there was no miscalculations. I mean, there's always a possibility that, hey, I marked it wrong. It really was 11.1, not 11.0. But no, these are the answers. These are the values. So it's not a miscalculation. That's a hypothesis. It's an educated guess, which I'm shooting down. So what's the other possibility, or what's the other answer that you had?
Is it just, I know there's a saying or something that no statistic is perfect or anything like that. So just to account for that.
That's not it either. And it's not dropouts. We'll consider dropouts to be in there as well. We're not missing anyone. Huh? So
I was about to say the teachers, and then you said you're not missing anyone, so I was like, oh, never mind.
Wait, what? Say that again?
The teachers?
I'm sorry, I'm not understand. It's very, your voice is blurry, if that makes any sense. It's hard for me to hear what you're saying. Did anyone else catch that?
Sounds like ET.
There's like an echo.
Yeah,
like
yeah,
the
you can type it out.
teachers.
I couldn't quite hear what you were saying. Teachers. Oh, is that professional? Is teachers professional? Maybe that's it. Am I a professional? Oh my God. It's crazy. I'm a pro. Love it. But no, again, we have, oh wait, no, education, that's teachers. I'm sorry. Crap, I'm in there. Right? Teachers are in education. So no, we have everyone. The answer is that every one of these numbers was rounded to the first decimal place. And when you round numbers, It's not exactly 11.0%. It's not exactly 10.9% and 14.9% and so on. So when you have all these numbers rounded, the rounding can be in such a way that at the end of the problem, you're off by a little bit because of what we call round off error. Round off error is the small error due to rounding intermediate steps. So if I would have gone and actually kept every single decimal for every one of these categories, then it would have added to 100%. I would have had them all. But because I rounded, then, I mean, think about it. Let's say there's let's say, you know, it should be 4.6% and 4.1% and 1.3%. Let's say I had 3 categories. Then if I round it to the nearest whole, this will go to 5%. This would go to 4%. Okay, crap, that doesn't work. Well, I tried to come up with an example off the top of my head and it didn't work. That adds to 100%. But the point is that sometimes when you add numbers that are rounded, you get a little round off error at the end. So if they don't add to the exact number, that does not automatically mean you made a mistake. It doesn't mean you didn't. So you should always check. But sometimes at the end of the problem, it just doesn't add to exactly 100% because of rounding error.
Is it possible to have rounding error with when you're 2 decimal places?
Yeah, because everything past the second decimal place might cause the rounding mistakes. Right? I mean, it could be at any stage of the process.
Oh, so even if it's like instead of 10.9, it's 10.98, and all of them have the 2 decimal.
You might end up with 99.99% as your final answer. You'll have an extra decimal in your answer, but it's still not going to be exactly 100% because you still have that little bit of rounding.
Because you're basically rounding all numbers all the time.
Exactly. So
Okay.
I always, tell my students, I go, when you record data, you record it to a certain number of decimal places because you don't want to give someone, hey, here's my response, and it's a number this long. You give them a nice truncated number that it's easy to read and comprehend and work with. But when you go back to your calculator and you actually continue with the steps of your calculation, you want to use all of those decimals because you want maximum accuracy throughout the problem. So you might record intermediate steps with fewer numbers, but at the end of the problem, you want to use all of them for maximum accuracy. Now, because this particular variable is categorical and not quantitative, I know that I should be using a pie chart or a bar graph to visually display it. Which of those two do you think might be better in this scenario? The pie chart or the bar graph?
Pie chart.
Bye.
So 1 second, hold on, before we go any further. In this class, if I ever ask a question, which is a multiple choice or a true false or something like that, I'm always inherently, apple pie, hello. I'm always inherently asking for an explanation as well. So if you say pie chart, tell me why. If you say bar graph, tell me why. If you say both suck, tell me why. If you say I love both, tell me why. Either way, give me a reason for your answer.
I would say pie chart just because I know that pie charts are for categories specifically, and since this is split into 10 different categories, a pie chart would fit best.
Well, wait a second. Bar graph is also for categories.
I think it depends on the data.
Well, hold on. Well, I said for this case, but 1 second. The question was, I pie chart because it's categorical, but bar graphs are also categorical. Right? So that's the question. I mean, they're both categorical, but I could, in theory, use either one. And I'm asking, is there a preference for this case? And if the answer is no, that's fine. But I'm asking what you think. So, Josue, did I get that right?
Yeah, you're good.
I get it? Okay.
Yeah,
So what is
don't worry about it. So I would say a pie chart mostly because all pie charts add up to 100%. while because like a bar graph, yeah, you can have like certain percentages in it. It can always vary, but like a pie chart, you're never gonna have like half a pizza when you buy a pizza, you expect the whole thing. You don't get
I
half.
buy a pizza, I do eat the whole thing, so,
Yeah.
but, I mean, I hear you that a pie chart adds to 100%, but bar graphs also add to 100%. It's just, it's not as obvious that it adds to 100% because you actually have to count, okay, this plus this plus this plus this plus this, but they do add to 100%. So there's some more like 3 hands raised, and I am reading people's comments as well, but people whose hands raised, go for it. Alex, what do you got?
I'm gonna have to go with the bar graph because it might just be me, but I feel like it might be a little too cluttered if it's on a pie chart.
Okay, so that's what I'm thinking as well. If you have lots of categories of a pie chart, it's not impossible to read. And of course, if you have your pie chart taking up the entire page, then it's, you can label them pretty easily. But if the pie chart is, just a portion of the page and you have lots and lots of categories, sometimes it can be hard to fit them all in. Also, it could be hard, like if you have 2 categories, like 11% and 10.9%. And I say, which of those 2 slices is bigger? Is your eyesight really good enough to distinguish between 11% and 10.9% of a pie? Whereas for the bar, it's a lot easier to look at 2 bars and say this bar is slightly higher than that bar. So personally, I think the bar graph is preferable in this case for both of those reasons. But it's not wrong to use a pie chart. You can still use it. You can use a categorical or a pie chart. Because I'm seeing some answers here. Samantha said a pie chart is an easier description of how they're all divided and equal to 99.9%. It's easier to see that they add to 100% for a pie chart. There's no question about that. But when you're looking at a categorical variable, you're basically trusting that it's 100%. Otherwise, it's not a valid distribution in the first place. But again, a lot of statistics is personal preference. Some people really like pie charts. Or maybe you go on Excel and you're writing a report and you say, well, I really want to use a bar graph here, but I don't know what command to use. So I'm just going to make a pie chart out of it. It's not wrong. Does that make sense? What I'm saying? Does this seem reasonable?
So there's no distinct difference between either or. It's
No.
literally as long as you can justify it.
As long as when you look at it, you as the reader, you as the presenter, you're doing a report for your business, you have a big meeting with your bosses and colleagues. When you present it, you want the people reading it to be able to read it and read it correctly. And if you feel that you can do it with the pie chart, knock yourself out. If you feel it's easier with the bar graph, or if one, for whatever reason, lends a visual flavor that the other one does not, then use that one. There's no definitive, yes, this one is better. But I think we would all agree, if you had 100 categories, you probably won't want to use a pie chart. So there's certainly a point that I think everyone who has some statistical sense would say the pie chart is not appropriate for this one. Where sometimes it might go the other direction. But in general, you can use either one. Does that make sense? Does that seem reasonable? Yes, no, maybe so?
Yes, Professor.
Okay. So now let's go to the other types of variables, which are the quantitative variables. So right away, we have a problem with quantitative variables that we did not have with categorical variables. And that problem is that whereas with categorical variables, I know all the categories, and I can immediately tell how many fit into each category. If I'm dealing with a quantitative variable, for example, let's say I'm calculating, or I'm interested in the average weight of everyone at CISA. Suppose that's my survey, that's my interest. What is the average weight? I think, is the freshman 15 a real thing? Is that what it's called, the freshman 15? In my case, it was the freshman 50, but still, is the freshman 15 a real thing? Okay, so I'm gonna go on the first day of everyone's freshman year. I'm gonna ask every CSUN student how much they weigh. It's anonymous, of course. And then on the last day of the semester, I'm gonna do it again because I'm really interested to see what the average weight gain or loss is throughout the semester. How many freshmen are there at CSUN? Anyone know roughly how many freshmen there are in any given year?
Like 520,
10,000?
10,000.
It's like
Yeah.
10, it's like 10,000. There's like 40,000 people at CSUN. So it's like 10,000. Maybe it's a little less. I don't know if graduate school skews that, but let's say there's 10,000 freshmen. There's a lot of freshmen. So when I ask all of them, and let's say I have a great group, they're all like, oh, a statistics survey? Yeah, this is very important for science. I'm going to answer this one. I'm not just going to throw it out. I'm going to answer this one. And we get 10,000 responses. How many different weights might you get? I mean, if I say, I want you to be as accurate as possible, then we're talking about what, the 10th decimal place? Right? Oh, 100.2. No, I'm 100.3, 100.4, 100.5, all the way up to 200, whatever, point, whatever. There can be thousands of answers.
You might get even 10,000 different answers.
Well, but I'll have repeats for sure. But there's still a smallest number and a largest number, right? So if I go by the 10th of a decimal, 0.1, 0.2, and so on, there's still like 1,000 different answers that I might possibly get. So how do I collate all that information in a way that is easily discernible?
You round it.
Well, you could round it. That's always a choice, 100%. And again, I'm not going to say it's wrong depending on the situation. But what we do is a little differently. So for a histogram, what we're going to do, because it's quantitative, I can do graphs. I like graphs. Can't really do graphs much with a categorical variable. The best I can do is just label them, this category, that category, and so on. But what I'm going to do with weights, let's say, is, and I wouldn't necessarily do this for weights, every 100 pounds or whatever. But what I might do is I might take all of the values that fall between 25 and 50, or between 50 and 75, or between 75 and 100, and say, I don't care about the actual value. I'm just going to combine all of them together into one group. Okay, thank you, Victor. All of them together into one group. And I'll say that all of the ones that fall between 75 and 100, there's whatever amount. And I will make what looks like a bar graph. I will make a bar to represent the total in that class. I have the lower end of the class. I have the upper end of the class. And I just drop the specific values. I lose them. And I just lump them all together into one group. And then I'll say, okay, between 100 and 125, I have that many, whatever number this is. And between 125 and 150, I have that number, whatever number that is. So with a histogram, what we're doing, it looks like a bar graph, but there's some differences. One, the bars are not separated. The bars are touching each other because one class ends where the next class begins. There's no gap like there is with a bar. This category separate, this category separate, this category. No, the bars for a histogram touch, they align. Now, suppose by some miracle, there was nobody between 150 and 175, I would just leave that blank. I wouldn't skip it and pretend it's not there. I would still have the space on the x-axis from 150 to 175. I just want to draw a bar there. So you don't skip a spot because you don't have any data for that spot. Yeah, question?
So Professor, sorry, I'm just trying to wrap my head around it. So a quantitative variable would be like one sum of something. It's like a lump because there's no, like you said, There's
Well-
no like gap, sorry, there's like a specific number, correct?
Well, I don't want to deal with 76.1 and 76.2 and 76.3 as separate values. There's too many of them to worry about.
Yeah,
I'm gonna take everything between 75 and 100 and say it falls in this lump here. There's this many in this lump, make a bar that high for that lump and ignore the specific values where they came from.
So
I
it's
have,
not
yeah, sorry, go ahead.
so it's not precise.
It's very imprecise in comparison to a categorical variable display. It's correct. I have lost a lot of information. If I asked you what the average height, the average weight is of if you see some students, and I'm doing it from the histogram, it's not going to be very accurate because I don't know where they are between 75 and 100, between 100 and 125, and so on. I have lost that information. The information is gone. So a histogram is a nice visual display to get a basic grasp of the situation, but it's very imprecise in comparison to the others. Very imprecise. And then again, there's the question of, well, how wide should I make my classes? If you make your classes a given width and someone else does a different width, your histograms could look nothing like each other. Which one's better? Well, they're both fine. There's no rule that says how wide they should be. That's up to you. So someone mentioned earlier that statisticians can lie or can skew data. It's not that we're lying as statisticians. It's just that out of all the choices that we have of presenting the data, we pick one that lends itself to whatever argument we're trying to make. Someone else can look at exactly the same data and come to a completely different conclusion because they presented it a different way. And neither one is more accurate than the other. It's just the way that you look at the data. Does that make sense? This is where you nod and smile and say, of course, right? This makes perfect sense. How can anyone not get this, right? Does that make sense? Yes?
Yeah.
Now, you have to choose also. When I say 75 to 100, do I mean this? Or do I mean this? What's the difference between these?
Is one of them absolute?
What do you mean by absolute?
If that wasn't the right answer, then I don't know.
Well, it might be, but I don't know what you mean.
Me neither.
Okay, good talk. So,
The square bracket means that it's including the 100.
okay, and the parenthesis, well, for the second one, you mean?
Yeah, for the second one.
Right, so the question is, suppose I get a value exactly at 75 or exactly at 100. Where do I put it? Do I put it in the bar just to the left? Thank you, Victor. Or do I put it in the bar just to the right? Well, it depends. If you choose to create your histogram with your classes having bars on the left, that means that 75 would go into that one. Whereas if you have your bar, your brackets on the right, that means 75 would go into the previous one. Which one's right? Again, I don't care. There's no right or wrong. We just want to make sure that you don't count 75 twice and say, put it in here and there. You got to pick your histogram and make it consistent across the entire spectrum, where if you fall on the border between one bar and the next, between one class and the next, then you make sure, what do we mean by going right or left? Well, do you know in basic algebra, if I have a number line and I ask you to graph 3 bracket to 4 parentheses, do you know how to, what I mean by that? So that means I'm looking for everything in here. So I'll go my number line to 3 and I'll go my number line to 4 and I'll shade in everything between 3 and 4 because everything between 3 and 4 is in there. Is 3 in there?
yes.
And the answer is yes. If 3 is in there because 3 is given by a bracket. Is 4 in there? No, 4 is a parentheses, so 4 gets a circle. That means 3 all the way through 3.9999999999999 and so on, as far as you want to go. They're all going to be in there, but 4 itself is not.
Professor, in the case of
Yeah.
bracket 75 comma 100 parentheses,
Yeah,
then it would be everything except 75.
no, the bracket indicates that we include it. So if you get 70, if you're doing it this way, then 75 lands in there. If you're doing it this way, 75 will land in the one to the left. Because
Okay.
75 is not in parentheses 75 to bracket 100. It's not in there. We don't include 75 when you have a parentheses. It's in the one to the left. Whereas if we use the upper version, then if you get 75, we do include it. It's the one on the right.
Professor,
Philip, that's what I meant. Yes?
for the second one,
Yeah.
you would include 100 into the
Yeah, for the second one, I wouldn't include 100 in that one. I mean, I wouldn't include 75, but I would include 100. For the first one, 100 goes to the right. All right, the next one over after this one is 100 to 125. So 100 would go, if I got 100, exactly 100, 100 would go into this one. Does that make sense?
Yes.
Again, that's your choice. You pick whether you want to use left bracket, right parentheses, or left parentheses, right bracket. But whatever you pick, just be consistent the whole way through.
Professor,
Yeah,
so in the case of the first one right there, the bracket 75
100, yeah.
comma 100. So then for that one, it would be everything except 100.
Well, everything from 75 inclusive to 99.999999999 would go in there. And then once you hit 100, now you're in the next one. Up until 124.99999999999. And then once you hit 125, bam, now you're in the next one.
So then for the bottom one, it would be 76.
No, 75.00000000001. Right? You don't start at 76. You start at 75, just plus a little bit.
Okay.
Right?
thank you. Yes. Sorry, I genuinely, this is the first time I've ever I've never heard of this. So I'm just
Never heard, really? In algebra, you never did parentheses and brackets? Wow.
maybe I don't remember it at all, but yeah,
It's one of those things where they say it and then it's our problem.
Well, everything's your problem. It's called life.
Oh, okay.
No, I mean, I teach high school and I certainly, they didn't explain good. Well, that's apparently they didn't teach you grammar either because they didn't explain well, but let's not even go there. But nevertheless, I know there's a fly behind me. I'm trying to catch it for like a half an hour. But I mean, we can certainly take a 2-minute break and deal with the algebra of the number line, where you have all these points somewhere in the number line. I'm sure you've learned the real number line. And if I want a collection of points, I would use braces. So if I use the braces 1, 2, and 3, that means this point and this point and that point. That's the collection of 3 points, 1, 2, 3. But if I want all the points from something to something else, like if I did 1 to 2 with brackets, then what do I mean 1 to 2 with brackets? What I mean is that here's 1 and here's 2, and I want everything between them. And because I'm using brackets, I'm also including the numbers 1 and 2 themselves. Whereas if I said 1 to 2 in parentheses, then what I mean by that is everything from 1 to 2, but not 1 and 2. That doesn't just mean 1.5. There's lots of numbers between 1 and 2. From 1.000000000, 1,000 gazillion 01, all the way through 1.999999999, till the end, till the day you die. Just keep saying nines over and over again, and you still haven't gotten all the way. But not 1 and 2, those are not included. So we use parentheses to not include a point, and we use brackets to include the point. Does that make sense? Yes,
How do you memorize that? Is there like a special trick you use or?
well, conventions are just things that you memorize. We memorize that brackets mean include, parentheses mean exclude.
So kind
Yeah.
of like I don't know how to explain it, but I remember like my last semester for math class, we did this with like graphing points.
Yeah,
So like,
this is graphing. That's what it is.
oh, okay.
It's exactly what it is. So in our case, if I have my histogram and I have, 5 and 6 and 7 and 8 and so on, and I want to make my bars representative of how many fall in each of these categories. Let's say I have some data that looks like this, and somebody comes along and says, "Oh, wait, I'm sorry, don't make it yet. I forgot one data point. A 6. I left out a 6." And you go, "Oh, okay. 6. Well, where should I put the 6? Do I put it in this one, 5 to 6, or do I put it in this one, 6 to 7? Because it falls right on the border. Where do I put it? And you say, huh?
Yeah, sorry.
Yeah, and you say, well, it depends. Are your borders 5 to 6, 6 to 7, 7 to 8? Or are your classes 5 to 6, 6 to 7, 7 to 8? I got this.
If it was bracket,
What?
oh, sorry to interrupt.
No, the 5 went away. It's okay. So it depends. So in the first case, if I did my brackets on the left, then 6 goes into that category and it goes into the middle one. If I did my brackets on the right, then 6 would go into that one. They go into the first bar. It depends on my choice. Which bar includes the 6? Is it the middle bar because I have brackets on the left? Or is it the first bar because I have brackets on the right? Whichever way you choose, that's where you put the 6. Does that make sense?
Yes, professor.
Yes, professor.
Rest of you, Jacqueline, does that make sense?
Yeah.
Okay. Everyone else?
Yes.
Yes.
Okay.
Yes.
All right. That's like 3 more people than I usually get, so that's great. All right, so that's histograms. Make sure your histograms have the same width for each class. You don't want to have different widths because that will skew your visual perception. If they have different widths, you might start to think of them differently. We only want one thing to matter, and that's the height. So the width should be the same, the color should be the same. You don't want to have anything that will skew your perception other than the height, which is representative of the frequency of the number in each category. Here's one on page 23. If you look at it later, it's a histogram of height of the percent of on-time high school graduates. And these are the number of states. The number of states in America and percent of high school on-time grads. And it's a little jump here, and then it starts at 55, 60, and move this down a little bit. Oh. 65, 70, 75, 80, 85, 90. And it has a basic shape like this. It's a little more accurate, of course, from the book. But it looks something like. It looks something like that. Now, when you look at a histogram, bless you, Joab, Joe, bless you. Why are we blessing him?
He sneezed.
Thanks, bro.
Then bless you, Job, for sneezing. So, when we look at a histogram, there are a few things that we look out for. What do we look for? What the hell? What do we look for in a histogram? What are the general things that we look for? One, we look for the shape. Now, in this course, we are going to have essentially three shapes. We're going to have symmetric, left skewed, or can anyone guess what the other one is? This is tough, I know, but I have a feeling.
Right skewed.
Right skewed.
Wow, you guys are so good. Right skewed. So symmetric, left skewed, or right skewed. Symmetric doesn't got to be exactly perfectly symmetric on the dot, but basically symmetric means that it's a mirror image across the center. So if it's symmetric, it essentially means that the left half and the right half of the histogram are essentially the same. This histogram on the page above, is this a symmetric histogram?
No.
You'd
Not-
left.
Not even close. It's not even close to being symmetric. Well, we'll get to that in a second, but it's not even close to being symmetric. So symmetric essentially means the left and right sides are approximately the same. So this is not a symmetric graph. Left skewed and right skewed is essentially which side of the histogram has the tail. Okay, if it's a tail on the left side, like ours is above, then we say that is left skewed. So a left skewed graph, it extends further on the left, would be a left skewed graph. Can anyone guess? And again, I know this is tough, but I have a feeling that you can do it. Does anyone know what a right skewed graph would look like?
The right skewed is gonna be the like exact opposite one. It's gonna be extended like to the right side.
Right, exactly. Extends further on the right side. There is a formula, by the way, for histograms where you can actually compute the exact skewness, which we're not going to do in this class. So there is a way of actually quantifying skewness and not just symmetric, left skewed, or right skewed. In this class, it's symmetric, left skewed, or right skewed. Again, it does not have to be perfect. If my histogram is slightly off, don't say, oh, well, it's not symmetric, it's not a perfect image. As long as it's ballpark. Any question that you have in a quiz or a test will not be vague enough that there's more than one possible answer. The example on my screen is left skewed. It extends further on the left. This is a left skewed histogram. So the first thing we look for is the shape. The next thing we look for is,
Professor,
yes,
what if there's so you know how the high part is on the right side?
yeah.
What if there's a high part on the left and right?
Is it like this?
Yeah.
Because that's symmetric again,
Oh, okay.
right? That's a mirror image,
Okay.
right?
Yeah.
Now, if it looked like this, oh, what the hell did I hit? Oh, Phew.
You have Clash Royale?
Yes, okay, I play it, all right?
I play it too.
Okay, I can't stop playing it.
Yo, Clash
Me
Royale is
either.
so
It's like
fun.
chess.
Well, it's not go crazy. It's not- That's just
I love that game. I used to have Clash of Clans.
that's just silly talk.
Ooh, wow.
Wait, what's your like your main push?
Bro, I think I have like 4,700
I'm
trophies.
only like. That's mine. That's mine.
But yeah. Good night.
All right, so what can I do? All right, shut up. Back to statistics now. Okay. Where's Bell? I've only been playing for like a week. There it is. So a friend of mine's like, you gotta play this game. I'm like, I can't. I got too much to do. He's like, you gotta play it. He's like, just play 5 minutes here, 5 minutes here, you'll be fine. I'm like, okay, now it's like 5 hours here, 5 hours there. What an asshole. Anyways, okay, center. Okay, here we go. Center. The next thing is center. Now, what is the center of a histogram? Here's the easiest way to think about it. I want you to imagine that your histogram is a physical construct, that you have built this wooden or steel figure. And I want you to balance it on one finger. Where would you have to put your finger underneath this histogram for it not to tip one way or the other? That's what we're going to call the center of the histogram. In this case, if you had to take a guess, doesn't got to be perfect, but if you had to take a guess as to where your center would be, where would you put it?
Say around 80, 85.
Well, I think 85 might be a little too much in the other direction, but yeah, I would say right on somewhere around 80. I would say is probably ballpark around 80, correct? So the center is essentially the balance point. I'm just going to say the balance point. If anyone reads this later and just says the balance point, what the hell is that? They're not going to get it, but I explained it in words. I'm just going to say the center is the balance point. It's the point where you balance it on one finger. Now, once like skewness, there's a numerical way of getting the balance point, although it's a little harder for histograms because, as we already mentioned earlier, you lose some of your precision when you lump them into classes. But you lumber loon with the but you could at least get a ballpark quantitative value from this idea. Leave. Did he leave? Is Lumberloon a bad card? Is that what you're saying?
There's no lumberloon. There's a lumberjack.
It's when you do a lumberjack and a balloon. It's
Ooh, so when the balloon.
Oh, a
if it's
lumberloon, a lumberjack and a balloon. It makes so much sense. It's crazy. I hate balloons. They suck. Anyways, okay, that's 2. Not they suck. I don't want to use them. They suck whenever I have to play against them. Anyways, question 2. Okay, the balance point. Let's move on. Come on, stats. Don't get me monologuing here. Number 3. Next one is the spread. We are going to have multiple ways of thinking about the spread. But for now, essentially, the spread is min to max. Not max minus min. We're not looking for a number. When I say the spread, I'm basically saying, oh, it's 55 to 90. That's essentially what I mean by the spread. Okay. I know where my center is, and everything goes between this number and that number. So the spread is just the min to the max. And the last thing that we look for are outliers. What's an outlier? An outlier is some data point or multiple data points which just do not work with the rest of the data. Imagine I had a histogram that looked like this. You know, you had Here's 1, here's 2, 3, 4, and you had, this, and then this, and then this, and 5, and then out here at 10, you had this guy over here. So you have everything lumped between 2 and 5, and then you just got this guy out in the middle of nowhere at 11, 10 and 11. It's just, what is that? What's it doing over there? It's so different than the rest of the data that it's just an outlier. Now, sometimes outliers are just mistakes. Oh, whoops, I put in a 10, I meant a 1. Whoops. Sometimes they're mistakes. Sometimes they're legitimate. And when they are legitimate and they're supposed to be there, depending on the situation, sometimes you might say, okay, I know it's a valid data point, but it's skewing the representative data point so much that I'm going to ignore it in my analysis. And other times, you don't ignore it. As you get better in statistics and you learn more sophisticated techniques of analysis, you'll have a better idea of when do I ignore it, when do I not ignore it. But for now, we're just talking about recognizing that the outlier exists. And like the center, like the spread, like skewness, there is a quantitative way of finding out whether something's an outlier. And we will actually do that in chapter, I think it's actually chapter 2. It's not that far off. It's coming up. It's not that far away. We're going to actually quantify outliers. Is this an outlier? Well, let's do this little mathematical technique and I'll let you know. So, questions so far? This is where you say no, yes, or
Not yet.
not
Nope.
yet. Not yet. That'll work. That's implying you will have a question later. I like it. Okay. So that was all about stem plot. About histograms. All this is about histograms. So let's now go on to the next one, which is a stem plot. A stem plot is our next visual display of quantitative data. And I want to do an example of one, but I don't want to write a million numbers. So, and unfortunately, I don't know why. Anyone, a Zoom experts, when I try to share my screen, it says allow Zoom to share screen, open system preferences, go to security and privacy to grant access. But when I do that, I can't figure out how to grant access. Anyone know? This is a Mac.
Aren't you sharing the screen right now?
No, I'm sharing my iPad right now. I want to be able to share my computer screen. And I don't know how to do it. It's really annoying. It used to work. I don't know why. I don't know why it stopped. Among the many things that I'm good at, technology or figuring these things out is not one of them. Oh well. Okay, so I'll just make up an example. Suppose I have the following data: 13, 20, 20, 24, 27, 30, 31, 31, 42, 42, 51, 62, 70, 94, and 122. So suppose I had that data. That's, for whatever reason, I took some survey, some poll, something. And these are the results that I got. And I want to display them. Now, a histogram is really mostly useful when you have lots of data. So you want to lump them together because looking at everyone individually is time consuming. But if I only have 15, 20 points, whatever this is, then I might choose a stem and leaf plot instead. And what I do there is I make a vertical line. And what I'm going to do now is I'm going to put on the left of the line, starting from the lowest to the highest, the numbers other than the last digit of each data point. So for 13, I'm going to ignore the 3 and just put a 1. For the 20 or the other 20 or the 24 or the 27, I'm going to ignore all those last points and just put a 2. 31 and 31, that just gets a 3. 42, 42 gets a 4. 51, 62, 70. Even though there's nothing within 8, I will not leave it blank or skip it. I'm still gonna write it. Then 9, then 10, then 11, and finally 12. So those are my stems. These are my stems. And then after the stems, I'm gonna put my leaves. So with a stem of 1, do I have any leaves?
3.
3. With a stem of 2, do I have any leaves?
You got 2 zeros, a 4, and a 7.
With a stem of 3, do I have any leaves?
0, 1, 1.
How about 4?
2 2s.
Oh, where are
5?
these numbers coming from?
1.
You tell me, where are they coming from? This is
I
the whole
kinda-
idea. This is the whole idea of a 7-leaf plot. Where are these numbers coming from?
My
So
Zoom
the,
like broke out. I didn't catch a lot of the explanation.
I understand. So what I'm gonna do is I'm gonna repeat every word twice. That way, if you miss half of them, you'll still be fine. Will that work?
Maybe.
Okay, okay. So okay, I'm done. I can't do it anymore. All right, so the leaves are the last digits only. And I don't repeat a first digit. So the first digit of 2 has 4 leaves. 2 0, that's 20. A second 2 0, another 20. A 4 for 24, and a 7 for 27. Then I have 30, 31, 31, 42, 42, 51, 62, 70, 94, and 122. This is my stem and leaf plot. Notice it's kind of like a histogram sideways, or I can like rotate this, and it's kind of like a histogram. Right? It has my numbers, and it has how many fall in each stem. Think of it like a tree, right? Here's a tree, a really horrible looking tree with a bushy thing on top. And here's a stem, and you got these little leaves, right? These leaves are on the stem. And here's another one, right? And leaves, and that's a horrible leaf. But you know what I'm saying, right? And here's another one, leaves. So, and there's one with no leaves. So a stem and leaf plot is essentially comes from like imagining a tree. You have all these stems, and each stem has a number of leaves. So the last number is always a leaf, and everything else before it is a stem. That is correct.
In
And
what circumstance would you prefer a stem plot over any other like graph or anything?
yeah, I mean, I prefer this over a histogram. I mean, imagine you did a histogram here. Let's look at the same data in a histogram, and you tell me which is better. The first question I guess I should ask is, what are your classes going to be for the histogram? Let's even do it by tens like we have here. So 0 to 10, 20, 30, 40, 50, 60, 70. Ran out of room, so the power of the iPad. Yeah. So I look, it's like getting a cell phone for the first time. Like I don't know what I did without it until I got it. Of course, you guys all grew up with, oh man, see, this is amazing. Watch this. Watch this. I'm gonna make it smaller. Yeah, that's what I'm talking about. Yeah. And 120. So from the 0 to 10, we have nothing. From 10 to 20, we have 1. From 20 to, oh man. So from 20 to 40, 2, 3, 4. 4 times as high. And then 30 to 40, we have 3. And then we have 2 from 40 to 50. And then we have 1 again. And then we have 1 again. And nothing in the 70 to 80. Actually, 50s, we have 1. 60 to 70, we have 1. 70 to 80, we have 1. Nothing in the 80 to 90, 90, 90, 100, we have 1. And then 120 to 130, we have 1. So, which of these do you feel is a better representation of the data, the histogram or the stem and leaf plot, and why?
I guess it's easier to concentrate the variables with the stem plot. You can tally up how many there are.
Well, I don't know.
I mean, and I know the numbers are still there on the histogram too. It just looks, I guess it looks cleaner.
yeah, well, Philip said, and Alex said the histogram looks nicer. Although, I mean, Alex said it looks nicer, and Philip says they're flipped. Those are both correct. The histogram looks really clean. They're really the same thing, but there's one major difference that makes the stem much more valuable than the histogram. And it's not necessarily that it takes less time. I mean, taking less time certainly should be a factor, but there's something about the stem and leaf plot that makes it superior to the histogram for this example. Alanis?
In the histogram, our outliers in some people can make it seem like it's a mistake. And in the stem parts, we weren't talking about outliers.
Oh, I mean, I look at this data here and my first instinct is I think that might be an outlier. Right? I mean, it's so far away from everything else. I mean, I don't know. I can see both of those just as easily, to be honest. Yo, what do you mean, Joe, whatever, God damn it. Whatever, Jay, what do you mean by accuracy?
It's more accurate. The stem plot is a lot more accurate than
Why?
Because the histogram is it's not getting the exact points.
That's it. In the histogram, we know we have 4 data points between 20 and 30. What are they?
I have no idea.
We don't have that information in the histogram. We've lost it. In the 7 leaf plot, they're 20, they're 20, 24, 27. I know exactly what they are. And I'd much rather have the data than not if I could. So when you have a small number of data points, the stem and leaf plot is usually superior for that reason. Whereas if you have hundreds or thousands of data points, then lumping them together into a histogram is going to be much better. Does that make sense? Does that seem reasonable? Yeah, no, maybe so.
Yes.
Okay. And sometimes you'll have 2 histograms that you want to compare to each other. How do I compare 2 histograms? I can't overlap them. So what I'll do is I'll put one histogram kind of like below the other. But with stem and leaf plots, you could actually have a situation where you have your stems and you'll have your leaves here. And what I can do is I can have a second collection of leaves on this side, and I can look at 2 stem and leaf plots side by side. And it's a lot easier for me to compare them when they're side by side like that than it is when one is directly beneath the other. So there are situations where I might prefer a stem and leaf plot, and there are situations where I might prefer a histogram. Also, sometimes you might have a situation where you split your stems. And I don't want to write this, but I do want to share it. So I'm going to hold this up just so you can see what I'm talking about. And then later, eventually, we'll have the book, everyone, so we can see it. But if you look at this stem and leaf plot, look at those stems. What do you notice about those stems?
The repeating.
They're repeating. So each numerical stem is put twice. So what's the difference between the first row for each stem and the second row for each stem?
The greater number.
Be more specific.
Can you
number
repeat,
than
please?
5.
Yeah, the upper stem would be 0 to 4, and the lower stem would be 5 to 9. So we split up. And my stem and leaf plot, we split it up so that 0s to 4s and 5 to 9s are separate. And this is if the stem and leaf plot is getting so big that it's kind of being unwieldy because there's too many data points, but not millions, or to the point that I want to use a histogram. I might separate it into a split stem and leaf plot where I do the first 5 digits, 0, 1, 2, 3, 4 for the first stem, and the second 5, 5 through 9 for the second stem. And it's basically the same thing as taking the histogram and separating each class into 2 new classes, right? I can go to the same histogram situation and do 10 to 15 and 15 to 20, and then have one here and none in the next one, and so on. Right? You can make a histogram where you also split each class into half the size. That's essentially what you're doing with a split stem and leaf plot. You're doubling them up, so making them a little easier to read. Does that make sense?
Professor?
Yeah.
So in the case of repeating numerical values, in that case would it be better to use a histogram over the stem and leaf plot?
It depends. There's no, I mean, basically the rule of thumb is if there are so many data points that the stem and leaf plot is hard, switch to a histogram. That might be 30 points or 40 points, certainly hundreds and thousands. Whereas if there's fewer data points and you can do it by hands, the histogram, the stem and leaf plot does not lose the information that the histogram does. So we want to use it if we can. We only switch to the histogram when the number of data points just becomes too much. Does that make sense?
Yeah, but if we were to break it into I don't know what you call it again. If we break it into with two different stems of the same number, what did you call it?
It's a split stem.
Oh, split. If we put it into a split stem, would we still wouldn't that create, I guess, more work because we would have to be comparing both stems that are repeating?
Well, I mean, it's not more work. You're writing the same digits that you wrote before. You're just putting half of them on one line and half of them on the other line. But you're not writing twice as much. You're just writing in two different places. Right?
Mm-hmm.
So it's really the same work. It's just a little more wieldy so that you don't have so many numbers in one line that you lose track of how many you have. Right?
Yeah.
It's not, if you're having, if you have some deeper questions in this, you're going to see as you go through the homework that you're overthinking this because it's just a basic idea. They're pretty straightforward. I think I'm not saying you should treat it flippantly. But I think some of these questions that you might have are just like questions that you don't need to worry about. And hopefully when you get to the homework, you'll see that. And if not, of course, feel free to ask. But that's it for stem and leaf plots. Dot plots we will get to later. But essentially all a dot plot is instead of a bar, you make dots. So for the same situation as this, I wouldn't have a bar. I would say 10 to 20 has this collection has 1 dot, and 20 to 30
Professor, can you scroll down real quick?
is not visible. 30 to 40 would have 4 dots, and 40 to 50 would have or did I do that wrong? No, I did it wrong. 20 to 33 dots, right? So a dot plot is like a histogram, but you just use dots instead of a bar. A dot plot. There's nothing different versus a histogram. It's just a different way of doing it. And again, you would not use a dot plot when you have hundreds and hundreds and hundreds and thousands of data points. It just is not, it's just too unwieldy to do it that way. But if you have a few, go ahead and use it. But we'll never use a dot plot. In this class, histograms and stem plots all the way. And the last idea for chapter 1 is a time plot. And a time plot is very different than histograms, dot plots, stem plots, and everything we've done before. Because everything we've done before, we have lots of individuals and we take our values and we see how many of them are here and how many of them are here and how many of them are here and how many of them are here. With a time plot, you're looking at one individual and you're looking at the individual over time. So a time plot is, well, a time plot of a variable plots for each observation against, not for, just plots each observation, sorry, plots each observation against the time the variable was measured. Can anyone give me an example in real life of a time plot? I know last session people brought up the idea of stocks. People definitely do time plots of stocks to kind of make predictions. I've certainly seen those. But let's go even more basic. You know, if you watch Grey's Anatomy every week, because everyone watches Grey's Anatomy, what do you see? What kind of time plot do you see every week on Grey's Anatomy?
When are you talking about the
Sex,
EKG?
fight, or
Huh?
That machine, you know, that reads your heart rate?
Yeah,
Yeah.
the EKG, what is it? Electrocardiograph? Right? So you're measuring some value over time, and it goes up and goes down, and you know, whatever, you know, heartbeats, etc. So time is on this axis, and your observation, whatever they are on the y-axis. And you're looking, what are you looking for? You're looking for trends, right? Looking for trends. You're looking for trends. You're looking for cycles. You're looking for, you know, looking to make predictions. About future observations. Right? And this is a stock thing. And you analyze a stock over the last 10 years, and you see every December it goes up, and every February it does this, and every this it does that. And, you know, and you hope that nobody else has noticed the same thing, and you buy or sell based upon your observations. And I personally don't do this stuff. It's not anything that I'm interested in. But I can imagine certainly people who are really into the stock market are constantly looking for situations where they notice things that others don't, and therefore take advantage of, you know, that kind of thing. So, anywho, are there any questions on chapter 1, the easiest chapter in the book?
Compared to all the other chapters, how much harder does it get?
Well, the other chapters certainly get more mathematical. And for me, that doesn't make it harder. That actually makes it easier. Because when you're just talking about descriptive terms, sometimes it's hard really to pinpoint, you know, precise ideas. Where when you have formulas and you have data and you're calculating things, as long as you know the correct formula to use, you get an exact answer, you know what it means, you interpret it correctly, and everything makes sense and goes forward. In that regard, I find this chapter to be the hardest chapter because it's the least mathematical. But in the other regards, I find it to be the easiest chapter because it's only descriptive. So it can really go both ways depending on what your strengths are going to be. I personally find it to be the easiest chapter in the book. Just because there's no calculations, there's no requirement to perform complex, you know, math.
But most of the complex math and calculations is done by the calculator anyway.
That's correct. But you have to understand what to put into the calculator based upon what you were given. It's not like it's going to say, turn on your calculator, hit this button, and over here put in this number, and over here put in this number. It's going to give you a bunch of stuff, and you're going to have to say, oh, okay, we're going to do a 2-sample t-test here, and there's going to be this many degrees of freedom based upon the information that was provided. And I know this, and my null hypothesis is that. So here's what I'm going to put into the calculator. and here's what I'm gonna calculate and have it do, and the calculator spits out your answer. Now, for me, that all made sense, everything I just said to me, because obviously I teach this stuff. So to me, it's trivial to do all that stuff. But if you haven't learned it yet, that sounds like what language is that? So once you learn how to do it, it's very simple. But if you don't actually learn how to do it, then it's a foreign language. So your calculator will do everything, but you got to know what to do, what to tell your calculator to do, and that part's the complicated part.
Professor, I keep getting an error message when I try to do the Macmillan learning thing.
Yeah, I had a meeting this morning to set it up, and I integrated the course, which means when you look at your Canvas screen, you can at least see that Macmillan is attached to it. And apparently I didn't go far enough to confirm that it worked, because I don't have the student view. So when you click
are y'all looking at a book right now, or I just got here, so I'm a bit.
No, we're not looking at a book. This is my iPad.
All right.
So, so by hopefully tomorrow, I'll send out an email tonight, and they're usually very quick about responding. Hopefully by tomorrow, that particular issue will be fixed. But on the Canvas page, again, if you go to announcements, there will be a link to setting up the homework, and you can go directly to that Launchpad website and get a free trial. And you'll have access to the ebook and to the homework. When I finish hooking it up, you don't have to go to that website anymore. You can get there directly through Canvas. Until then, or even after then, you can do it directly by going to the homework website. So in fact, you know what? Let me see how many people so far. First, I'm going to stop recording.